Hey everyone, and welcome back. Today, we're jumping right into an absolutely fascinating microscopic matchup. We are looking at two distinct metal structures that, they might seem completely identical on the surface, but down at the atomic level, they are engaged in this intense clash of physical properties. So, let's not waste any time and dive right into the structural showdown between austenite and ferrite. Okay, before we really get into the heavy science here, I've got a quick question for you to test your intuition. Which metal structure do you think conducts heat better? I mean, we generally just assume that all iron conducts heat beautifully, right? We use it for cooking pots, engine blocks, old school radiators. But what if I told you that the actual microscopic crystal structure inside the iron drastically changes its ability to move heat around? Keep your guess in the back of your mind as we unpack this. Let's formally meet our contenders. On one side, we've got austenite, which is pretty commonly referred to in metallurgy as gamma iron. And on the other side, we have ferrite, also known as alpha iron. Now, the wildest part about this whole thing is that we are talking about the exact same base material here. It's just iron, but their unique internal atomic architectures make them behave like completely different, almost totally opposite materials. All right, round one, the thermal conductivity showdown. First up is ferrite, and you can really think of this one as the ultimate fast pass for heat. Because of its specific atomic arrangement, it acts as a remarkably efficient conductor. When you introduce heat to ferrite, it doesn't dilly-dally. That thermal energy just passes right through it, almost immediately. And that makes ferrite incredibly predictable and stable, even when temperatures are fluctuating wildly. So that brings us to the next part of the story, the microscopic secret inside austenite. And here is austenite's big, defining secret. It features what we can basically call the empty center. This is this crazy structural anomaly where the metal crystal has a very tightly packed, dense exterior surface, but the very center of its formation is completely hollow, literally empty. It's a quirk that completely alters its physical mechanics. Imagine having this tough, dense outer shell, but a complete void right in the middle of the crystal lattice. So how does that empty center actually play out in the real world? Well, heat enters the dense outer layer of the austenite, but instead of passing cleanly right through it like it does in ferrite, it finds its way into that void and just gets trapped. Because that dense outer layer actually acts as an insulator, austenite effectively becomes a microscopic thermos. It literally just pulls the heat inside rather than transferring it away. And the mathematical reality of all that trapped heat is pretty staggering. Because austenite acts like a tiny thermos, its thermal conductivity absolutely plummets. In fact, austenite has only 1/3 the thermal conductivity of ferrite. Just let that sink in for a second. By merely changing the arrangement of the iron atoms to include that tiny empty center, the metal loses a massive 66% of its ability to conduct heat. Which naturally leads us to our next major factor, thermal expansion rates. This brings us to a really vital engineering consequence. When we measure this, ferrite sits at a thermal expansion coefficient of roughly 12. But austenite, it jumps all the way up to 17. That means it's expanding roughly 1.5 times more than ferrite under the exact same heat. Now, in precision machinery, that difference is absolutely massive. We are literally talking about the difference between a high-performance engine running smoothly and a critical part binding up and completely failing. Let's really connect the micro to the macro here, just to make sure this is crystal clear. Ferrite releases heat quickly because of its structure, right? So naturally, it experiences minimal thermal expansion. The energy simply doesn't stick around long enough to force those atoms far apart. But austenite, on the other hand, traps that heat internally in those hollow centers. This causes a huge energy accumulation. The atoms get extremely energetic from all that trapped heat, and the direct physical reaction is a significant outward expansion. So the lower the thermal conductivity in this case, the higher the thermal expansion. All right, let's wrap this up with our final takeaways. So here is the final scoreboard for our structural showdown, and it all comes down to the idea that structure dictates function. Austenite's empty core means it has poor conductivity, just 1/3 of ferrite's, simply because it traps the heat. And all that trapped heat, it results in a massive expansion coefficient of 17, compared to ferrite's nice, stable 12. It's honestly kind of amazing how a microscopic empty space can completely dictate the behavior of the heavy metals we rely on every single day. So I'm going to leave you with this thought. The next time you see a piece of metal warp or bend under intense heat, ask yourself, is it just getting hot,
Or is it that secret empty space inside expanding against its will? Thank you so much for joining me for this explainer. Keep questioning the invisible world of materials around you, and I'll see you next time.